So today we are going to talk about OPTIKS, which is an optimized key transparency system. And if you don't know what that is, don't worry, we'll unpack it over the next few minutes. So this talk is going to be about key distribution and key verification in end-to-end encrypted communication systems, in particular end-to-end encrypted messaging, also meetings, but not so much, we'll not focus so much on the meetings. So in end-to-end encrypted communication systems, to verify that you're talking to the right endpoint, you're getting the public key or the right endpoint, you usually have some form of QR code scanning or checking security code. So what exactly is that? So if we look underneath the system, so the point of end-to-end encrypted, say, messaging is that when a message is, Bob is sending a message to Alice, the message is encrypted on Bob's device, and even though it is passed through a service provider, it is going to be decrypted on Alice's device, and the service provider should not be able to decrypt and read it. And there is a complex ratcheting protocol that goes on underneath, but the fundamental thing that needs to happen before this protocol starts is that Alice needs to get Bob's most latest public key, and Bob needs to get Alice's most recent public key to establish a secure channel. Now, how do they get each other's recent public keys? Notice also that these keys change when you reinstall the app or change the device. And in all current deployments, the service provider, for example, Zoom or Meta or anybody who's providing the end-to-end encrypted messaging service, also maintains a key directory and distributes the public keys on behalf of the users. Now, this is obviously a problem. Why? Because now, without any further verification, the service provider can do an undetectable meddler in the middle attack. What that means is the service provider could generate a pair of secret key public key pair and then provide its own public key to Bob, saying this is actually Alice's public key, which is a fake key, and likewise to Alice. So now what will happen is essentially the service provider has established a channel through it. So it can decrypt all the messages that come through this, read it, and re-encrypt it back to the other devices. And without further verification, it will go undetected. So the more traditional approaches to enable verification, and today afternoon there was a talk from Felix on this, is to do QR code scanning. So that's one way of doing this authentication, where you can have the devices next to each other and point to the devices to scan the QR code to make sure you are seeing the correct key. There's other variants of it, like safety string. In case of meetings, it's security code. It's a little more subtle, but there is some variant of it. But unfortunately, this is not a very usable solution. People also don't use it very much in practice. So key transparency tries to automate this process so that the users manually won't have to verify. The client app can do some verification in the background to verify that the correct keys, they're getting consistent keys. Key transparency has been around for almost a decade by now. So the first, actually, even before the academic literature started on this, the first deployment was by Keybase in 2014, even though it was not meant for encrypted messaging, it was for PGP key distribution. So the privacy requirement was slightly different. Since then, there has been a long line of work in industry and also in academia. There's also an IETF working group that's trying to standardize transparency protocol. So, and today we are going to talk about OPTIKS, which is yet another key transparency system. So one question is, why aren't all the problems solved yet? So no, and they're not, and there are a lot of problems, but with OPTIKS, we do the following contributions. So if one thing that you would take away from this talk is the OPTIKS is the most simple key transparency system so far. It's very simple and efficient, easy to understand. And then we give an OPTIKS extension which supports multiple features that has not been looked at in deployments before, such as reducing storage, caching, account decommissioning, and then we also present a split architecture that makes the implementation very scalable, and we can apply it to other designs as well, and Kim will talk more about it. Okay, so for a quick overview of the system, the way the key transparency systems work is the following. So the service provider still maintains the key directory as in the traditional systems now and do the key distribution. But in addition, they also post a periodic signed commitment to the public key directory it maintains periodically. Where it posts, I'm going to talk about in the next slide, but the important thing is all the parties in the system should see the same commitment that they're posting. And when Bob is looking up for, say, Alice's public key, Bob should get a cryptographic proof along with the public key, which the Bob's app will verify in the background to see that it's getting a key that is consistent with the posted key directory commitment. Likewise, Alice should also monitor her key history, and which is basically getting a cryptographic proof, and her software will also verify that this key history is consistent with the latest commitment that is posted. And where is it posted? This is generally an open question, but you can think of it as if it's posted on a blockchain, which is a very heavyweight solution to it. Two like third parties, like I think Amazon is what the Meta WhatsApp implementation is using. So there's a variation here, but for the purpose of this talk, it's not important. All right, so if that's a high-level overview of the system. So now let's look at the core cryptographic primitive that is required to. So just a quick comment here. So the timer just went into 15. All right, okay, all right. Okay, so the core cryptographic building block here is something called the append-only directory commitment. So in the paper, there are multiple layers of cryptographic abstraction with ordered zero knowledge set and history dictionary and so on. But this is, for the purpose of the presentation, let's look at this more simplified abstraction, which is what is a directory. A directory is a list, a collection of label value pairs where the labels form a set. And in the context of this key directory, this label is going to be username appended with a version number. And the value is going to be the public key. That's going to be for encryption. Okay, so directory commitment is a succinct commitment to a whole key directory, a short commitment to the key directory that the service provider can compute. And the important properties of this commitment is that the service provider can later prove that a certain element X with a version number belongs to the underlying directory, or that it doesn't belong to the underlying directory with respect to this short commitment, non-interactively and privately, meaning it doesn't leak, the proof shouldn't leak anything else about the set. Now the directory commitment we will be requiring, and is usually required in almost all key transparency systems, is append only. So that means nothing gets deleted from the directory. And it also has this additional property that given two ADC commitments C1 and C2, the service provider can generate an append proof that one of the underlying directories is a subset of another. Now this is constructed using very simple cryptographic blocks, which is a Merkle hash tree and a verifiable random function. But I'm not going to go into the details of that because that will require more time. For the purpose of the talk, this abstraction is enough. You understand this abstraction, that's enough. Okay, so our core protocol, the OPTIKS core, is basically the service provider maintains this key directory, which is all the key versions of each user. Say Alice at version number 1 at epoch T1, Bob at version number 1 at epoch T1. Later, Alice replaced her key and added a key pKa prime. So that's also added to the directory and so on. And at every epoch, the service provider publishes this ADC commitment, which is a commitment to this directory. Now, the more interesting part is how lookup and key history works in this case. So what is lookup? So lookup means, let's say Bob's, in this tiny example, Bob's current key version is at version 2. So lookup means when another user, say Alice, wants to look up Bob's key history. So the service provider returns the current key of Bob along with a proof. And the proof is basically the membership proofs for all the versions up to the latest one, so version 1 and 2, and the non-membership proof for the next version with respect to this commitment, with respect to this ADC commitment. And when Bob does his own key history, the checks are very similar, except that along with the proofs, the actual keys are also returned to Bob. Okay? So why does that work? It's very simple to see, and the reason is, say, so we are with this example with Alice. Bob's current key version is at version 2. So when Bob did his key history, he got these proofs, right? Membership for version 1 and 2 and non-membership for version 3. Now let's say when Alice is looking up Bob's key, if the service provider tries to provide a stale key, like an old key, say like version 1, then basically it has to show a non-membership version for version 2, whereas in the key history proof it shows a membership version. So that directly contradicts the soundness of this cryptographic primitive, ADC. You cannot, for the same username version, have both membership and non-membership with respect to the same commitment. And likewise, if the service provider tries to add a fake key, say version 3, which doesn't exist, and tries to show that for Bob to Alice, a similar contradiction will arise. Now in the opposite direction. So Alice will have to see the membership proof for Bob, while Bob sees the non-membership for that version number. So in optics extension, we also extend, so this is the core optics protocol, very simple and clean to understand, but you see like here, you have to actually check out all the key versions up to the latest one. But if the clients could do caching, you can do better than that. So which we added in the OPTIKS X, which is say, if the client could remember the last key they have seen for a particular user, then they only have to see the newer keys. And yeah, not the new ones. And we also added another thing of this in optics extension to mitigate the problem of this ever-growing storage. Since the data structure is append only, we added the notion of time period, which is a fixed system parameter. And from one time period to next time period, you can see like in this example from the yellow to the purple commitment, the directory gets compressed. So all the older keys are thrown away, say Alice's key version 1 and 2, only version 2 is promoted to the new directory. And within the time period, the optics code, the way we were doing before works. The only requirement is that now user has to come online during a time period to check that their key was promoted correctly. There are many more extensions but I would refer to the paper for that. And with that, I'll go on to the implementation. Kim?
All right. So just very quickly, since we're pretty low on time, we have a new kind of system architecture compared to prior work. So we do this split kind of architecture where, as you can see in this diagram, there's the client devices, there's a service provider who's essentially just a router that routes the queries and the updates to these appropriate REST APIs. So we have logically and actually physically separate query service and update service. The query service interacts with the database that stores the directory and basically just responds to the query requests. The update service is very simple REST API that simply queues the update requests into the database. And then we have a repeatedly triggering update task that pulls the queued updates from the database, creates the directory update and kind of new commitment, and pushes it back to the database. And this kind of split architecture gives us a lot of benefit because it allows us to use a different memory representation for the query service and for this like update task, which are the heavy components here. So for example, for the query service, we can use basically a hash table kind of cache to store only some of the directory data. Whereas for the update task, we have to keep everything in memory. And what you can see here is that we get really great query throughput. So this is really benchmarking the full solution end to end. And we get something like 4,400 queries per second on 1 million size key data set. And now you can see how the curve goes down. Of course, these become heavier and the communication size becomes essentially the bottleneck here. And on the update side, we update, always update in batches of 1,000 updates. So it doesn't really make sense to update just one at a time. So we batch them. But in any case, this gives us several hundred updates per second. And even for very large key directories. And you can see also there, the gray area is an interquartile range for these epoch times. So epoch is how long it takes to insert these 1,000 new updates there. So this ranges something like from 1 second to maybe the average is like less than 4 seconds. The performance is mostly in database operations. I think in all of these kinds of key transparency systems, it's mostly in the database operations, database writes in particular. So if someone is really good with databases, come talk with us and we can maybe improve this like a lot. We compare to two particular prior works, Parakeet and Merkle Square. For Parakeet, we have actually full system comparison because Parakeet offers such, but it's very kind of complicated. So I'm just going to refer to the paper. For Merkle Square, we can actually more reasonably compare this core ADC primitive to Merkle Square, although here are the numbers, of course, like orders of magnitude better and this and that. It's a little bit weaker security model though, and we have an implementation, and thank you.